All right, so I'm going to be talking about some applications of complex numbers within control systems. There we go. So control systems are a type of engineering, sometimes called control engineering, control systems engineering, and it is a branch of engineering that talks about designing systems. So this could be multiple machines, this could be computer chips working together. But it's a system where we want a certain behavior within a controlled environment. Control systems are in just about every automated thing we use. Um, so laundry machines, cruise control on a car, autopilot on a plane, even something as simple as the flush of a toilet is a engineered system um, that we are going to call a control system. So to start with some complex background, and these are things we've all discussed in class, but the idea of a function, a mapping of a input of complex numbers to an output of complex numbers. So here, each zero of the input function causes the output to rotate around the origin. So if there is 1 0 in the input function, it's going to go around once. If there are 2 zeros in the input function, it's going to rotate twice in the amount of time this function, the input function, goes around once. So there is a connection between the location of zeros in the input and the actions of the output. Um, and so if there are no internal zeros, so if we look at this function, the 2 zeros are just outside of this input box, that means the output function does not rotate or include the origin within its bounds. So that was talking about zeros, but now to talk about poles a little bit. So this is an example that has a 0 and a pole. The 0 is at -1. The pole is at 0, the origin. Um, if the input function just circled the 0, then the output function would circle the origin. If the input function just circled the pole, then the output function would also circle the origin, but in the opposite direction. And so the poles definitely do have a large effect on the output function, as we've seen in this class. But here, where the input function, which is this orange box around the graph here, that is our input function. Well, it goes around a 0 and a pole. So that means that our output function does not circle the origin. The 1-to-1 ratio here kind of cancels out, and instead it kind of this horseshoe or wishbone shape that just skirts the origin and does not circle it. So that's just a little bit of kind of how zeros and poles act within input-output functions in the complex plane here. So starting to connect it into the systems, the Nyquist contour is a contour in the complex plane that has a large effect on control systems engineering. So it is a semicircle centered at the origin that covers the entire right half of the complex plane. So here we show it with a radius of probably about 1.5, but the radius is actually infinite. So it does not have the bounds we see here. It would actually continue and cover the entire side of the complex plane. So stability. So the Nyquist contour is important because it helps explain or determine if a if a system is stable. So if a function has poles on the right half of the complex plane, and that means within that Nyquist contour, the system will be unstable. It's because the poles on the right side of the complex plane have an increasing value. They cause the system to increase, accelerate out of control, which is very unstable. An example like this would be to try and think of a physical example. It would be like if a force was acting in the same direction as gravity. So if we have gravity pulling something down and then also another force pulling something down, and if there were no counter forces to balance those, that object would accelerate um, accelerate forever. Excuse me. So in reality, we have forces to counteract that. We have air resistance, and eventually the ground will hit that. But if we had kind of, this infinite idea where gravity and another force are both acting in the same direction, they would accelerate out of control. And that's kind of what happens when a function has poles on the right half of the complex plane. So to get around that, we can provide feedback within the system. We can provide a balancing force. So what that would look like mathematically would be a horizontal shift on the original function to move the pole out of the contour. Remember, the contour is the entire right half, so a vertical shift is going to keep it on the right half still. It would have to be a horizontal shift, moving it out of the Nyquist contour and then applying stability. A little bit more about feedback. So this would be an oversimplification, but if we had some function f of z that was unstable, it had a pole in the Nyquist contour, then we could provide feedback, which simplified would kind of create this rational function f of z over a constant plus f of z, where k is some constant. Excuse me. If f of z had poles that are poles on the right side that created that instability, now this horizontal shift with this constant here is going to move it so the poles are on the other side so that the input and the output are not having this friction causing this instability. So that is one example of complex numbers in the real world. The Nyquist contour was really interesting. I've been looking into that a little bit more as well, and just the plot you're able to create with a Nyquist contour is just a really simple, easy way to check for stability in the system. So that's a pretty, fun fact about complex numbers here. I did want to make sure and cite the main source I used for this, a YouTube video that really helped explain a lot of the topics I discussed here and is where I got several of my images I used here. All right, thank you. And I hope you enjoyed learning a little bit about control systems.